And so we did see the mirror lab. So there in the on the left-hand side, there's actually a mirror that's still in the mold. Let's give it sort of the white color. There's a bunch of stuff up underneath that it sits on, kind of gives it the honeycomb structure. Anyway, that's a mirror that's actually been made, but it hasn't been fully polished yet. Right next to it, although I couldn't get into the same picture, was the one on the right side there with the blue on it. That's blue latex sealant. And once they get it all polished and all set up, they cover it with a latex to protect the surface. Then they box it up in this, they box it up in a big steel box for shipment. That's what they do. So anyway, and think that big tower that you see kind of above the blue mirror. That big tower has got lasers all mounted up in there, and that's how they actually measure how accurate the polishing is. They shine lasers all over it, and that tells them where all the high and low spots are. So if you're curious, they get it down to there's the high and lows don't vary more than 1/1,000,000th of an inch. So that's how fine a degree that is. It's pretty incredible how they do that. If they give us an analogy, they said if you were to expand that mirror to the size of the United States, that means across the entire United States, you wouldn't have anything higher than 1 inch. So that's how smooth those mirrors are when they're done. So they're pretty.
Lisa,
So the mirror lab was a lot of fun. We had a good time there.
you tell me when they started.
Well, so there we are in the lobby, and the guys got to tell us about some things in the lobby. And then we went through books of pictures. I could have spent all day looking at the Apollo moon photos. They were pretty incredible. Lots of different things. So, how many have seen Apollo 13, the movie? Everybody seen that? Okay, lots of you have seen that. No scene where they're getting too much carbon dioxide in the cabin. But unfortunately, the command module uses square CO2 filters, whereas the LEM uses round CO2 filters. So they couldn't switch them. So they had to kind of jerry-rig a unit to use square filters inside the LEM. Well, that's actually that little filter is in that little picture. That's the actual filter they used there on Apollo 13. I don't know, I just when I stumbled on that in the book of pictures, I just really was fascinated about that. By the way, one of my favorite movies. So actually, I have an autographed copy of that from the guy who ran Space Mission Control at the time. So we also went to the Science Center and Planetarium. So here's some of the group outside there. Just taking some pictures from there. I wasn't on that tour, so I can't say too much about it. But Alice did tell me that the Science Center was not that big real estate wise. It was just jam-packed with a lot of really interesting stuff she thought. And she said the planetarium show was quite fun. We were just hanging out all day with your friends doing different things. So there they are out there looking at a big sundial on the ground. We were never too old to play in a sandbox, so we were playing in a sandbox there literally. That sandbox, the thing that's multicolored there, that was actually pretty cool too. It was this box of sand, and they had a projection unit above it. And depending on the depth or the height of the stand in the box, it would color it from above different colors. So blue's lowest, then green, then it would go yellow, then orange, then red. And so if you took your finger and drew through the sand and made like a trench, the trench would change colors depending on the height and the topology of that trench. Plus, it would draw in real time then topology lines all around the sand. It's actually fascinating. A lot of us playing the sand for a while. So anyway, yeah, I'm 8 years old again. What can I say? So anyway, the stadium photo is just where we had lunch. We had lunch on the 5th floor of the stadium at a nice restaurant there. And one side you look down into the stadium, the other side you look towards the mountains down there in Tucson. It's very nice. There was, of course, food. We had a nice lunch. Very, very nice lunch, actually. Very nice venue. We all had a wonderful time. So. Like I said, I'm kind of got a twinkle in my eye about maybe doing a Lowell trip in the springtime. So stay tuned for that. The board approves that. I'll be setting up a Lowell trip for everybody.
Good evening. Really happy to talk to you guys tonight about smart scopes and specifically the ZWO C-Star S50. I've had it for a little over 1.5 years. Very easy to use, but like anything, there's tricks and tips that make it even better. I also want to share some shots that are taken with it. I'm just amazed at what this little thing can do. 2-inch lens, it's amazing. My wife Lisa and I, we live here in South Tempe, so we're at Bortle 7 or 8 sky, so it's very challenging. And also I've had cataract surgery, so I have mini monovision, 80% near and distant. So it's always been a little challenge for me for scopes. Um, like a lot of you, I've had several scopes, that have been around for a while. And my first one, 2001, was Dobson 8-inch actually, not go to. And it was great. And, the Jupiter and its moons and rings of Saturn was amazing. Inexpensive, very inexpensive to buy. I learned to star hop. But the cons were it's bulky, there was no tracking, so I was constantly trying to get the image back. And for me, with my eyes, smaller galaxies and nebulas hard to see. Um, Orion and Andromeda for me, I could see, but something smaller would be tough. From there, I went to the go-to scope and tracks objects. But again, heavy. And for me, the setup time was 30, 40 minutes, something like that. And if I did want to get into astrophotography, I was going to spend 500 to $1,000 on a hyperstar and have to learn some, you know, fairly intense softwares, GIMP and Cyril and stuff like that to post edit. So about a year and a half ago, November 2023, Starzona called me and told me that they were getting pre-orders for ZWO C-Star S50, and they were all getting them, and it was inexpensive, Bluetooth, really easy to use, has a camera integrated with it, does the stacking, sets up in minutes, and I went for it, and it's just been great. Um, it is very easy to use. I think almost just about anybody can use one. Um, the cons for it is planetary viewing is not really for that. Sun and moon, yes, but the only planets that you possibly could do would be Jupiter and Saturn, and you'd have to shoot raw, and you'd have to post edit. It is alt azimuth, so you are limited to how high up you can shoot. Um, but recently, ZWO came out with a wedge, so that can change it into an equatorial, and so I haven't done that, but that would be something interesting to do. The other drawback is the storage, and I can't remember if it's 32 or 64. It's not huge. It is capable, you are capable of saving all your pictures instead of letting the camera stack them. But if you do, it's going to take up room, so you have to be careful with that. Um, I'm going to show you. Okay, this is my 8SE, and then that's the C star. It's very small, uh, under under a couple feet. And here are the specs for it. I'm not going to go through every single one, but as you can see, it's really lightweight, 6 pounds, 2-inch lens, and it's got a camera in there, and it shoots in RAW, MP4, JPEG, stuff like that. So I'm going to go and show you some of the pictures I've taken with it, and I'm going to go through pretty quick. But I will tell you that most of these pictures are not touched up, but some are. And the ones that I did touch up, I just used like the Apple tools, um, and specifically the magic wand. It just kind of like, I think it's an AI thing or something, and it just colors it correctly. Pictures of the moon. This is Andromeda, and that was one of the first ones I took a picture of, and it just came up really quickly, and I was really wowed by that. And that's not touched up at all. Another Andromeda, and then we have the Dumbbell Nebula, and I don't believe that one's touched up either. Pac-Man, and this one I did invert, and I did have to color that, but I mean it's still pretty amazing that I could get a shot of that with this camera. And this is the Ring Nebula, and that's the colors that it came with, but I did magnify it because it was very small. And here's Orion, and this was actually shot in Santa Fe, New Mexico around Christmas. and it was very dark. I mean, I don't know exactly what Bordeaux sky, but I would think 3 or 4. And this was after 5 minutes. But Orion's a huge target and very bright. You can see with your eyes. So, but it's amazing. It came up like that in 5 minutes. And I was basically taking that picture to show the folks I was with how the camera works. And this is a picture I took from Tempe. And you can kind of see the Running Man in the top left. And there's the Running Man by itself. And so another thing that ZWO came out with a few months ago was a thing they called mosaic. No, they call it framing. We know it as mosaic. And basically allowed you to get a bigger shot. So I could get Orion and the Running Man in the same shot, which before I had to do separate because they're so big. It takes a little bit longer, but it's definitely worth it in my opinion. And this is a Sculptor Galaxy. I did have to color that one. Bode's Nebula. This is a horse head, and this is just an amazing thing for this camera. And you can see in the left where the Flame Nebula is, but I couldn't get it in before the framing. And that's the Flame. And this is with Mosaic. I got both of them in there, which I really liked. I wanted to get both of them in the same frame. And this is the same one, but it is degaussed, so it's a little more crisp, but it's different, but I think it's clearer. And Sombrero Galaxy, that's untouched. And this is the Eagle Nebula, and you can see the throne. I was just amazed. I didn't think this camera could get that picture, even though it is pretty big. I was pretty wowed that it could get that picture. And this is the Swan Nebula, and this is untouched also. And the Trifid, that's untouched. And the Lagoon, all summer nebulas. And this was one I really had difficulty with before. It's very faint most of the time, and I did have to color this with the Apple tool. This is the Western Veil, Witch's Broom, and this is the Eastern Veil. The Helix Nebula, I did have to color that one. And Thor's helmet, that's colored also. But again, I just can't believe I got this picture. This is the Monkey Head, Rosette Nebula. And you can also, when I was on this cruise with Sky and Telescope, and the guide was telling me that I can that it's kind of cool to take a picture of the transit of the ISS transiting the sun and the moon. And so I did this. It's like only a half a second transit. And it's really low, but I just put it on video and just picked one of the pictures. And as you can see the panels and stuff on that. And my next thing I want to do is I want to get it transiting the moon, and I haven't been able to do that yet. This is a picture of the comet. And the scope did have trouble finding this for some reason. So I had to pick a target close to it, and then it found it, but pretty amazing stuff. This is a accessory that's pretty necessary if you're going to be looking at the moon and sun, because it's hard to believe, but it has a hard time finding them. And this, you just look through the little hole until the sun or moon comes through there, and then you know you're aligned. And the other thing is this leveler. With the sun and moon, if it gets out of level, you have to lengthen and shorten the tripods to make it level, and it's kind of difficult. With this, you just spin the wheels, and so to me, it's worth the money. So anyways, these are the tips that I've come up with. And like I said, it's an alt azimuth, so things near 90 degrees are going to be tough. And also, targets that aren't in the database, you can enter the R and deck coordinates. I've only found a few targets that I couldn't find in the database. It's a huge database. I can't remember how big it is. Um, And like I said, you can shoot in raw images for Jupiter and Saturn and also other things and download it to your computer for post-processing. And it's fairly easy. The raw files can be transferred by computer by Bluetooth or cable. And as far as ZWO support, it's mainly by email, and I believe they're out of the UK. They respond in a couple days. They are based in China, so they continually request access to my photo library. But personal preference, I just take snapshots and go from there. There is a newer model, less expensive, S30. It was around 350 at the time. And by the way, some of the members were telling me that the S50s, some of their friends have got them for like $400. So they're really inexpensive. Um, and also a tip, if you're going to be taking solar eclipses, you have to take the filter on and off. So a tip is to just stand in front of it when you're taking it off and on. Also, the last tip, this scope has a light pollution and a nebula filter that's supposed to go automatically, and it usually does, but sometimes it doesn't. You need to either turn it off or on. Um, so anyways, in my opinion, this is a great tool for beginners and also a great teaching tool. It's not going to compete with James Yoder's pictures, but it's incredible for somebody like me. I like that these smart scopes can bring people into astronomy and astrophotography that were previously restricted by expense or learning curve. Uh, this S50 opens up a world of deep sky objects for many people, and I try to share it with my friends and family. Um, so anyways, that's it. I appreciate your time.
Right. Our next presenter here is Peter Monson. He's from Chiricahua Sky Village down in southeast Arizona. He's here to tell us a little bit about it. We got a little bit of echo going there, Jeff. So anyway, I'll turn over to Peter here, and you can go ahead.
Thank you very much, Steve. I'm very grateful for the opportunity to participate in the meeting tonight. To tell you a little bit about myself, I moved to Arizona 7 years ago. I'm a retired professor of chemical engineering, and I took up astronomy 6 years ago. So I'm looking at an audience that's probably mostly much more expert than me in some of these things. So the story tonight is about Chiricahua Sky Village, and Chiricahua Sky Village is about providing dark sky opportunities for astronomers, affordable dark sky opportunities. It's a place where you can go and have your own dark sky observing site, and you can do imaging, you can do visual, and you can develop the site in whatever way suits you. We are not a commercial organization. We are an LLC, but we are not a profit-making organization. We are organized very much like an astronomy club. So let's get that right out there. We are not a real estate program. This is about amateur astronomy and taking care of amateur astronomers. So the picture here is a kind of, what should I say, a table setter. It's probably, in my opinion, the best astrophotography image that's been taken at Chiricahua Sky Village. And it's a mosaic done by Ben Hakala. And it's showing the, I think you all know what it's showing. It's showing the Orion region. And it's a very wide field view. You can see the Orion Nebula. You can see the Horsehead, the Flame Nebula. If you're over here, you can see M78. You see the Witch Head Nebula over there. And all the wonderful Barnard's Loop and all of these kinds of things. And that image was taken over several days by Ben Hakala at Chiricahua Sky Village. How do I advance it? Oh, yeah. Yeah. So So what is it? So it's a communally owned 92 acres. Now, sometimes people have trouble imagining what 92 acres means. Well, if 92 acres is a square, then it's 600 meters on the side. So that gives you an idea of the scale of the operation. We have a very large area of land. CSV members, Chiricahua Sky Village members, buy shares in an LLC that owns the land. We started out by having a group of members who pooled their resources to purchase the land, and I'll tell you where it is shortly. And that created the general fund. And we used part of the general fund to purchase the land. And as we get new members, they pay their membership fees that go into the general fund, and the general fund is used to further develop the site. And once you've got your site, which the minimum site size is 5,000 square feet. And once you've got that, you can do what you like. You can put up a tent, stay in the tent. You can build an observatory. You can have an RV. You can have a cabin. It's what you choose to make of it. Now, we've got a new component that we've developed in the last year, and that's the personal remote observatory. Now, you know that there's a lot of commercial remote observing going on right now. There are companies like Starfront. What we offer is a unit that you build or buy, and it can house your equipment, and then you can use it remotely on your site to do observing. And we have two memberships for pros. We have a regular membership, somebody can put a pro on their site, or they can have a pro membership, and the pro can be put in a special area that we have. So that's the basic structure of what we're doing. Thank you. Appreciate that. So how did we come about? Well, members of the Seattle Astronomy Club just in Washington decided to see if they could find a communal dark sky site. And that led to the creation of Goldendale Sky Village. And that was led by our general manager, Christopher Smithies. And so they went to this place called Goldendale in Eastern Washington, and they found an area of land which is about 1/3 the size of Chiricahua Sky Village, and that's Goldendale Sky Village. Now, how many have been to Washington State? Beautiful place, isn't it? Except in the winter, it's very wet and cloudy. And so the members there started to think, well, maybe we could build another one of these in a place where you can see things in the winter. And that's what led them down to Arizona and Chiricahua Sky Village. So we have now about 50 members from 6 states, Arizona, California, Oklahoma, Oregon, Texas, and Washington. The reason I'm so happy to talk to you today is that we think this is a terrific opportunity for observers who live in the Phoenix area who might be interested in having their own dark sky site in a fairly inexpensive way. Plenty of room for growth. So where are we? Okay, so there's 2 maps here, one showing the southwestern United States, and then if you look at that little red square on the left, I've blown it up on the right. Can I get a pointer or something? Anybody have a pointer? What do you do? Oh, I see. Yeah. Okay. Oh, perfect. Perfect. Thanks very much, Steve. This is great. So this area then is where we are. So this is southeastern Arizona. And you can see Phoenix is up here, Tucson is here, and here we are just west of the Chiricahua Mountains. Now, where we are is geographically quite significant. There's an area of land that's mostly in Mexico. It's called the Chihuahuan Desert. And the Chihuahuan Desert is an area of about 200,000 square miles. And most of it is in Mexico. Good part of it is in West Texas and also in New Mexico. And we have a little corner of it in southeast Arizona. Now, the significant thing is that Chihuahua Desert is high desert. It's got an elevation of 4,700 feet. Where we are right now, the elevation is 1,000 feet. What does that mean? It means the climate's much milder than in Phoenix. So high temperatures in the summer, 85 to 100, and temperatures in the winter are 50 to 60. So it's much colder in the winter than Phoenix. It gets down to freezing at night, but you can still do observing or whatever you want. Travel. We're 40 minutes from I-10, 90 minutes from the Tucson airport, and 3 hours from PHX. From my house, which is in South Phoenix, it's about 3 hours, 15 minutes. So definitely an accessible place for people in the Phoenix area. Of course, everybody wants to know, how dark is it? Well, this is the contour map from darkskymap.com. As you can see Phoenix and Tucson here. And the gray, the various levels of gray mean it's dark. So where we are is in this gray area, and the typical SQM readings are 21.6, 21.7. We think of it as Bortle 1 to 2. I won't go any further than that, except to say it's plenty dark. You would be, I'll tell you a little story. I go down there, especially in the winter time. I get to my cabin, I go in, I have my dinner. Then I go out about 8 o'clock, start setting up my gear. And I look up, and I'm always overcome. I'm always just overwhelmed by the carpet of stars I've got. And now this is interesting. If you look at the picture on the left, that is an aerial view of CSV. And in the background, you see the Chiricahua Mountains. And in the forefront is where CSV is. Just want to give you a sense that it's very flat there. Even though we've got mountains on both sides, we've got this very high planar region, which means that we've got a very good 360 view of the horizon. And the second picture there at the top, I took with my iPhone. I did a panoramic view, and you can see that a very clear view of the horizon. And this was something I got very excited a couple of years ago, and then again last year. Most of you know that we can see some southern constellations from southern Arizona. And I got excited because somebody told me I could see Omega Centauri, which, as you know, is the largest globular cluster in the Milky Way. If you go to the southern hemisphere, which I have, but not since I've been doing astronomy, you can look up and you can see this thing with the naked eye. It's incredible. So what I did was I set up my 100mm Takahashi with a camera on it, and you can see that that's the orientation. I'm like 10 degrees above the horizon, and the image on the left is the image of Omega Centauri that I got. So personal remote observatories. This was invented by Blaine McCoy, who's a member from Seattle, Washington, and he wanted to do remote observing. He's also, like me, a retired chemical engineer. He's a very good engineer, and he did all the design. And this shows the first of the pros. It's basically a miniature roll-off observatory. But there's only room for the scope and the mountings. There's no room for the astronomer. And his first one has a solar panel array. And this shows the first telescope, which is an FSQ 106 Takahashi, which 106mm Hertzfeld refractor. And then now we have this area here, we have the pro area, where we now have, I think, 5 of the pros in this area, and they have common power supply from a big solar array that we have. So where do you stay at CSV? Well, you can just stay in a hotel. You can camp. You can have an RV. For instance, this is Bob and Mary Koch's RV. They bring it from Oklahoma. And they have little parties where Mary makes us hamburgers, which are the best hamburgers I ever had in my life. And we have this, which is actually, I should show you this one. Alex Beck is a member here. Some of you know Alex, is that right? Well, this is Alex's shed, and he has a telescope here, and he's now got a pro in the background. And then this cabin here is what we call the Stargazer Inn. It's a communal cabin that can be used by the membership. So lots of opportunities, and you can develop the site and use it in whatever way that you want. Okay, here are some aerial views. So the top left shows the gate area. These pictures came from Mark Orvek's drone camera. He did an overflight and then took pictures. The top right is what we call the local group, named after the local group of galaxies. It's a group of us have our cabins in the same place. And this shows my cabin here. And you see I have a solar array. And then I have concrete pads here, and I've got 2 telescope piers. I've got it set up like that so that I can I do visual as well as imaging. And I can have a telescope doing imaging while I'm doing visual astronomy. This shows the pro area, and this is a storage shed with a solar array. This has 2 pros, but there are now 5 there, and we've got new pro members joining once every few months now. This is Andrew Wolf's, he's got a shed, and then over here, he's got a custom-built observing platform with a concrete pier in the center, and he puts his 18-inch Dobsonian up there and does visual observing. Here we have Ken Tolliver has a remote roll-off observatory that has a shed. We have 2 kinds of membership. We have a regular membership. So you buy shares that entitle you to exclusive use of a lot, and you can do what you like with it within reason. And the minimum is 2 shares, and each share is 2,500 square feet. So some people have significantly more than that, but 5,000 square feet will give you something. Say it was a square, it would be like 70 feet on the side, which is plenty of space. And then the pro membership is for people who just want to have their own remote observatory. You won't be paying any more. You won't be paying monthly fees. You just, you pay the membership, and then you have to pay either to build the pro yourself, or we have a company, Simple Systems of Phoenix, which is owned by Andrew Wolf, and they will build you a pro for about $7,000. Okay, that's it. The picture on the left is a QR code, and if you hold your phone up to it, it'll bring you to our website, chiricahua.skyvillage.com. And I built the website myself with the goal of answering as many anticipated questions as viewers might have. And there's a place where you can send email in if you have inquiries. I'm very grateful for your attention. Thank you very much.
Do we have any questions for Peter? We got a few. Hang on until you get a mic so the folks on Zoom can hear you.
Yeah, but currently we use Starlink, but we're going to look into land-based internet. We're very remote there, so the kind of things that we take for granted up here, like Cox and all this other stuff, is just and Starlink has its features, but heavy bandwidth is not one of them. So our people who do the pros, when they're transferring data, they will wait several hours for the packets to come over like that. But of course, if it's happening overnight while you're asleep, it doesn't really matter. But we are looking to develop land-based internet connectivity.
I'm curious as to, you mentioned that you could basically do anything you want on your lot. Do you have to allow room for people to transfer or drive through your lot to other people's lots? And do you have like a CCR per HOAs where you prohibit people from putting white lights outside and things like that? Like,
well, we obviously have a low light policy.
Yeah.
And you'll hear about it very quickly if you were to be. What you kind of, I chose to be in the cluster. Remember what I said, if it's a square, it would be 600 meters on the side. That's a lot of space. So you can be remote or you can be near other people if you want. We have rules, but first of all, you can't have a structure that's more than 200, got to get this right, 200 square feet. So my cabin is just about 200 square feet. And the reason why that is that if you go larger than that, then Cochise County will want to start permitting and stuff like that. And so we avoid that. Well, if the tiny home was less than 200 square feet, yes, indeed, you could have whatever you like. Yeah.
is there a quantity of 200 square feet that you're limited to? Could you have like 10 of them?
I'm not sure I understand your question.
So are you limited to one 200 square foot structure, or could you have multiple per each share?
Yeah, I think you can have multiples, but there comes a point where you say, why would you want to do that?
Well, for example, I'm thinking about this club. So if the club wanted to purchase a share and have several cabins on it for members to enjoy.
I think what we'd be looking at is, rather than, my presentation here is meant to promote the idea of members of EVAC becoming members of CSV, not EVAC becoming a member of CSV, if you get my drift. Oh, we got one at the back, yeah.
So your electricity is solar. What about water and sewer?
What about what?
Water and sewer.
Right. Well, the question about sewer is answered currently by 2 porta potties. The question about water is answered by, you bring your own bottles of water. Listen, just to explain, we're facilitating astronomy, not luxury vacations in the desert.
Yeah, I have a quick question and just a comment. I remember
I
stopping.
think the microphone's off.
Okay. I stopped south of Safford, driving across country one time, 1986, which is like 50 miles north of there. And that's probably the best, darkest skies I've ever seen. So it's a great location. But my question about curiosity is, can you see Phoenix and Tucson sky glow from your side?
We do have some sky glow. We don't have a sky glow from Tucson, which is 80 miles away. We're probably getting one from the south, near the border. It might be from Douglas, and then possibly also from Benson. But just that Omega Centauri image was taken due south of, yeah, it's hard to be away from sky glows completely.
Okay, we're running out of time, so we're going to take 2 more questions. You're going to be one of them. One of them is online. Person online is asking, how many miles of dirt road to get into the place, and what's the condition of the road?
We've used dirt roads. We divided the area into lots, and then we have parks, which we haven't used much yet, but those are areas that where there won't be lots and that can be used for observers coming together for joint observing and things like that. I don't know how many I don't know how many miles of dirt road we have, but every lot is served by an accessible dirt road. So for instance, I brought in, I had concrete laid on my lot. So I had a concrete truck come in and pour concrete. That wasn't cheap, but, and then I had my shed brought in, and other people have had that. And that was done on the dirt road. And we take care of them. Okay.
Steve, thank you. Good evening, everyone. I'm Ted from Fountain Hills, here with my wife, Peggy. And tonight we'll talk a little bit about exoplanets. As you can see from the title of my talk kind of gives away the message. Oh, Steve, would you be able to tell me how to do that point red dot thing up here? So it turns out that in the analysis of distant stars and using the techniques I'll talk about tonight, the average star has more than 1 and sometimes more than 2 planets on it. So if you take all those hundreds of billions of stars in the Milky Way and consider that there are more planets in the Milky Way than there are stars, perfect, thank you. And then multiply that by a bunch of a few other galaxies in the universe, maybe 200 or 300 billion more. We've got more planets than we do stars, and so we'll talk about the possibility of of life in distant places. This is the big question, of course, that everyone wants to know. Are we alone in the universe? Are we it, right? Right now we have, the magic number is 1. We're one place in the universe that we know of where life exists. We are working really hard on the planet Mars to see if there had been a number 2 in the early years of the solar system. We don't know yet. We'd love to find out. I hope that we get the sample return mission from Mars working and get those core samples back here on Earth where we can look at them in detail. But this is the big question. So in 1961, Frank Drake came up with this equation we call the Drake equation. And basically, this is the number of planets that might be able to hold life in our galaxy. And so it's the product of a whole bunch of numbers. And as you remember from high school algebra, if any one of those numbers is 0, the number n, which is the number of civilizations whose electromagnetic emissions are detectable, would be 0. So we're going to talk about 2 of those numbers tonight. The fraction of those stars that have planetary systems and the number of planets per solar system that would have an environment suitable for life. So what we want to do is see whether we can determine here tonight, or by reporting on the investigations that have been done to date on finding exoplanets, can we constrain either of those numbers to be greater than 0? And that would help. We can't do much about the other ones, but we can talk about those too. So this is the idea, the general picture of solar system formation. We call it the nebular hypothesis. A large rotating disk of gas is perturbed by some nearby supernova explosion or something else like that. It begins to condense. It's spinning around. The physics causes the North Pole and South Pole material to condense down towards the middle. You end up with a disk of gas rotating. Eventually, the center of it condenses to a star, and whatever little bits are left over become places like Earth, Mars, and the planets around our sun. If the Hubble telescope has looked deep into the Orion Nebula and discovered that there are many places in the Orion Nebula that are in the process of condensing into these protoplanetary systems. So we call them proplids. These are the tiny disks of material that are forming all through the Orion Nebula, which is this huge cloud of dust and gas that we can see in the winter. And this is what a complex dust structure around an existing star looks like. These are direct images from the Hubble showing how a star in the center can be surrounded by a flat disk of condensing gas and dust, which is in the process of becoming planets. And there are folks at Lowell who are specialized in the analysis, the modeling of how these disks of material actually become planets and condense into individual planets themselves. The statistics are good so far. As of the last, about 3 months ago, we've got identified almost 6,000 what we call exoplanets. So planets around stars other than our sun. And you can see in the graph below, they tend to be in these various populations. So the way that you read this, along the x-axis on the bottom, that's the orbital period in days. So you can basically consider that as distance from the star. The farther you are out on the right in this graph, the farther your planet is from its star and the longer it takes to make an orbit. And then on the y-axis, that's the size of the planet that's been discovered. And so you can see in the upper left, very common are these things called hot Jupiters. That is a very large planet that's orbiting very close to its star. And that means that the odds that it will pass in front of its star and allow it to be detected are greater than they would be if it was much farther from its star. So hot Jupiters are among probably most of the planets discovered so far are giant gas giants that orbit close to their star. And then as you go down, there are very small planets that orbit very close to their sun, and we call those lava worlds. Essentially, these are small planets that are so close to their star that they might orbit in days, and they might even be molten for all we know. So this is the kind of distribution you have there. So tonight I'll talk quickly about the first 4 of these detection methods to find these exoplanets. The list actually goes on beyond the bottom of the page here. So we'll talk about radial velocity method, transits, direct imaging, and micro lensing. And then there are a whole bunch of other things, including actually some really esoteric technology for determining that there are stars, planets around stars, and in fact their mass and even some of their constitution as well. So the radial velocity method is one that takes advantage of the fact that a star that has a big planet orbiting it, the star is actually tugged a little bit by the planet, and the two of them they orbit a common center of mass, and the common center of mass can be inside the star, or if the planet is really large, it might be near the edge of the star. But the star will be making an orbit around the center of mass at the same time the planet is making an orbit around the star. So sometimes the star will be coming towards us, and sometimes it'll be going away from us as it makes this orbit. Now that depends, of course, on the plane of the orbit compared to us here on Earth. If the plane of that system is vertical to us, we'll never see a Doppler shift because the star will be moving like this. But if it is horizontal, then we'll have times when it's coming towards us and times when it's going away from us. And you can see in the lower right, this is an image of the orbital phase of one of those stars. Now, how can we tell if a star is coming towards us or going away from us? This is the part I like the best. You might remember that when a star is emitting light across the entire spectrum, and that light passes through a layer of gas that's cooler than the star, you see these things called absorption lines in the spectrum of the light from that star. So if you send that light through a spectrograph or a prism, it spreads out into the rainbow, and on that, and you can see that these little dark lines here represent the absorption of light of certain wavelengths by the material in this cool gas cloud that the light had to pass through before it got out to our telescope. Now, but it turns out that if the gas is hot and emitting its own light, forget it, no star in this case, now the gas itself emits light at the same wavelengths that the gas absorbed light when it was cool. And those are fingerprints of the elements that are in the gas molecules that gave off this light. So these fingerprints allow us to tell, like this is a spectrum of hydrogen, and those of you who have looked through a hydrogen alpha telescope at the sun during the day have seen that most of the light that you see is using this orange color that's one of the hydrogen alpha emission lines. And this is what that spectrum would look like from the sun. Lots of different elements in the sun, in the outer layers of the sun. And as the light from the sun passes through those layers of gas, various wavelengths are absorbed, and we see this fingerprint of all those gases in the outer layers of the sun overlaid on each other. And the job of a hydrogen alpha telescope, of course, is to throw away all of that stuff except that one orange line, so we can see that. So here's a little animation of that. And the secret is, now this picture is dominated by the big planet going around in the big circle, but ignore that for a moment and take a look at the star in the middle. Notice how the star is making that much smaller circle around the center of mass of this system. Well, that's what's making these little lines in the spectrum go back and forth. As the star approaches us, the light is shifted to the blue, the same way that sound from an ambulance gets a higher pitch when the ambulance is coming towards you. And when the star is on the right side of that picture going away, the light emitted from that star is redshifted, and it makes those lines move back and forth. And if you have a very sensitive spectrometer and you can look at with a microscope and measure the motion of these tiny lines back and forth through the colors over time, you can infer that the star is moving back and forth, and you can calculate the mass of the planet that would have to be there in order to tug the star that much forward and backward. And here's one of the first stars that was discovered to have a planet, 51 Pegasi. And you can see here the velocity of the star on the vertical axis on the left in meters per second. That shows you that the star is going towards us over here and away from us over here and back towards us over here. So here's a perfect example of one of those star systems where it's oriented almost perfectly horizontal to us, and that star is moving towards us and away from us. And this gave rise to this nice article in the New York Times, which basically said if there was a system with astronomers above our solar system and they were looking down on our sun, this is what the motion of our sun would be as it was tugged by the planets in our solar system. So you would be able to infer that our star has planets around it by monitoring the motion of our sun as it's tugged sideways by Jupiter mostly and the other large planets pulling on it as there's all these multiple orbits. So there's a lot that you can do. Now, if we have some physics nerds in here, you can understand this picture. If you don't understand it, I can take questions later on. So that is the radial velocity method. Okay, we'll skip that. So the second method is called a transit method, and this one is pretty obvious. You would understand this if you were to hold your hand up in front of a bright light at the theater. You would notice that the amount of light striking your eye went down depending on the size of your hand compared to the size of the spotlight shining towards you. And when a planet passes in front of its star, if it does pass in front of the star, and it's only a small percentage of stars where we're lucky enough that the planet actually orbits in a plane that passes in front of its star. But if it does that, we can actually measure the amount of light that's blocked by the planet. And so if you see this tiny dip in the amount of light emitted by the star, and it repeats at a constant interval 2, 3, 4 times, you have figured out that there's a planet orbiting that star, and now you know its orbital period, which allows you to infer things like its mass and the mass of the star, or at least the ratio of the two. And this method is used by the Kepler mission, by the TESS mission, and by ground-based astronomy as well. This is what a transit might look like from Earth. How many of you glimpsed the Venus transit back in 2012 or 2008? Yep, I came to Phoenix. That's when I first got interested in moving to Phoenix, and 2 years later, I ended up moving out here. I wasn't into astronomy in 2008, so I missed that one. But we do have Mercury transits as well, and the next Mercury transit is only 7 years away in 2032. So mark your calendars for that. Mercury's a lot smaller, but it's easy to see in a telescope with a solar filter on it, or an H-alpha telescope as well. So here's the transit method. If it's a large planet, a small planet, you get a small dip in the light curve. If it's a large planet, you get a much bigger dip in the light curve, so you can tell something about the size of the planet from the amount of light that's blocked by the transit. Here's the first transit measurements in 1999, and you can see that the data is not as crisp and clear as it was in that previous image. That's a simulation, but this was pretty good data, and it definitely proved that the method worked. And here's a system called TRAPPIST-1, and TRAPPIST-1 has multiple planets around it, and you can see that each planet, based on its orbital position, orbits either more quickly or more slowly than the other ones. And so we can tell that these planets are at different distances from the star, because the ones that have the longest dip are the ones that are orbiting the farthest from the planet and moving most slowly. And so we're really lucky that this system has multiple planets, and they're all aligned in such a way that they all pass in front of the star at various times. Back in August 2013, the IAU decided to invite the public to name some of these exoplanets, and you can see that they regretted this decision very quickly. This is some of these are my favorite. The jelly donut planet, permadeath, spherical disk world, emergency backup Earth. Yeah, I like that one. That's really good. Legoland. Anyway, this is obviously an XKCD comic. You can find it on the web, and it's worth a gamble. But you can also do this from home. I think we've got some people in the audience who might have done this already. Few people have done that. This is my friend John Gianforti back in Durham, New Hampshire, and John has confirmed exoplanet transits from his 11-inch telescope in his backyard in New Hampshire. He's not discovering them, but he's confirming ones that are already known to be those with rather large planets, slow-moving planets that give you lots of opportunity to measure the light curves from the planets. So John collects that data. So let's do some math. You're going to lock the door, Steve, so nobody leaves now. We have two math charts here. So the transit depth, which is the percentage that the light dips, is proportional to the radius of the planet over the radius of the star, and then square that ratio. So for the sun and the Earth, the sun's radius is 695,000 kilometers. The Earth's radius is 6,371 kilometers. And when you do the math, you see that the light of the sun would be diminished by 0.008% for someone out in space looking back at our system and watching the Earth transit the sun. That is a very, very small drop. But a transit of Jupiter in front of our sun would give approximately a 1% dip in the amount of light that was being received by that distant telescope. And that would be well within, we know that's well within our ability to measure the dip in the light emitting from the star. So we certainly think that other civilizations, if they were watching our sun, could infer presence of planets around the sun as well. Now, this is what we call an occultation. Now, a planet passing in front of a star gives you a very, very small dip. But in this case, an asteroid in our solar system is going to pass in front of that little star right there, the bottom one in these two. And keep your eye on that star as it drifts across the telescope screen. So that is a very dim asteroid now passing in front of that star in its little asteroid orbit as it goes around the solar system. And eventually it will uncover that star. And it's back. So this is called asteroid occultation. I always try to show these. We are always looking for more volunteers to come out into the desert with us, because the more people that monitor one of these across the very face of the asteroid, the more data we get on the shape and size of the asteroid and its orbital parameters as well. So that's something that, it's a group called IOTA, International Occultation Timing Association. And if anybody wants information on that, just let me know. You can also directly image some of these solar systems around different stars using speckle interferometry and other advanced techniques, so that you can actually directly image the fact that there are planets around these stars. And here you can see on the bottom, the Keck telescope is showing three different, there we are. Yeah, three different planets around this star with an occulting disk to block the light from the star itself right here. So there's B, C, and D. Each of the planets around a star is given a letter, and the letter pattern always starts with B. A is the star itself. And so B, C, D, E, and F, et cetera, would be the planetary letters, unless one of them is called Jelly Donut Planet. Same thing here. Here's a color picture of the same thing. Direct imaging of planets around distant stars. This is a real difficult thing to do. And here's 7 years of Keck telescope observations actually showing the orbits of those planets around this distant star. And so you can see the scale here is about 20 astronomical units in the center. So that's 7 years of data. Here's Beta Pictoris, 63 light years away, and we can actually see that planet over multiple years moving in its orbit around that star. So direct imaging actually works pretty well. And here's an artist's conception of what the debris disk around this giant star might look like if you were unlucky enough to be hung out in space there. Here's a little simulation of some of these particles So this giant disk flattens down as we saw before, and then over time, these particles begin to accumulate. As soon as two of these particles touch each other, that group of two particles has more gravitational attraction than one. And so just like dust bunnies under your bed, they begin to grow. And here you can see how these spirals begin to form, and eventually they coalesce into individual planets as well. Fomalhaut B is one of the earliest ones that I ever saw directly imaged, and we've got multiple years of data from the Hubble telescope showing how that planet is moving through the disk of debris around this star. You can see it in the tiny picture right here, and here are here's from 2004 to 2012, watching that planet as it orbits the star, which is hidden here behind this here. And lots of images of debris disks around distant stars. So this is really a successful technique. The micro lensing method, I got to tell you, this one is the strangest one to me at all. In this case, we are using we're here on Earth, and we are seeing a star, but we're not seeing this star. We're seeing the star behind it. And the gravitational attraction of this star in the middle is bending the light around it, right? Just like we call those Einstein rings. And it's bending the light around it so that as this star moves around, we get a light curve that looks like this, with a peak in the middle where the ring of light that's being bent around that star has maximized the light that reaches us. But if there's a planet orbiting that star, what you might see is this little tiny bump as the gravitational attraction of the planet adds a little bit to the light that's being refracted around that star by the gravitational bending of space, of space-time. And so this to me seems almost Buck Rogers-ish, but it's working, and it has been used to detect planets around other stars as well. Randall Munro also put together this 2012 graphic showing all the planets that had been discovered up until that point to scale. Very obvious that those big, giant, hot Jupiters dominate the picture, but you notice interspersed among these is lots and lots of tiny planets as well. The Kepler mission is the first mission to actually detect exoplanets from space. Kepler was launched in 2009, and it monitored the brightness of 150,000 stars up near in the constellation Cygnus every 30 minutes, looking for dips in the brightness of those stars. And of course, it was very successful. So obviously no atmosphere out in space, so Kepler could, as long as its gyroscopes were working, Kepler did a great job of staying pointed carefully at that set of 150,000 stars, and every 30 minutes captured the intensity of light coming from that star. So you had a light curve, 150,000 light curves to look at, and some of them had dips in them and a lot of them did not. You know, when we go back to our original understanding of the universe, we start with Ptolemy's ideas about how things were put together, right? That all the planets orbit Earth, we're the center of the universe, and the speed of the planet is constant. All the planets made perfect circles around us at constant speeds until Copernicus came along and suggested maybe that we weren't the center of the universe, right? Maybe the sun was the center of what was known as the universe at the time, but still believed that the speed of the planet was constant. But you had to explain things like the retrograde motion of Mars, right? As we pass Mars, it appears to go backwards against the background stars for a while, and then it continues to go forward. So this is a bit of a mystery, and you really have to figure that out. So Kepler used data from Tycho to come up with, of course, his planetary 3 laws of planetary motion, in which he replaced the circles of Copernicus with ellipses, understood that the sun was not at the center of the ellipse, but at one of the 2 focal points of the ellipse, And most importantly, that the speed of the planet is not constant as it goes around its star. Right? When the planet is closer to the star, it goes faster. And when the planet is farther from the star, it goes slower. That happens to us here on Earth as well. And Kepler's 3 laws of motion, you can see they orbit in ellipses. And the second law is one that I find a little reasonably easy to understand, that since the speed of the planet varies, when the planet is closer to the star, it's going faster. When it's farther from the star, it's going slower. But the area of these 2 triangles for equal amounts of time contain equal amounts of area. So the line between the star and the planet sweeps out an equal area in equal time, no matter where the planet is in its orbit. And we can use that knowledge along with Kepler's 3rd law, that's a little more hard to explain, to figure out what size planets are, how far they are from their distant stars, and so on. So there are some rules that planets have to follow, even around other stars in other solar systems. Here's a picture of the Kepler mission in theory and in fact before it was launched. This is a picture of the detector, 95 megapixels. That doesn't seem like a lot today, but it was for the day. And of course, all of that had to be operating in space. This is an image of the area in Cygnus that Kepler stared at for all those years. And its field of view was really quite small. But the idea was, let's just see if there's anything out there. So similar to the Hubble Deep Field, just look for a long time, very deeply in one small part of the sky. And if no planets had been discovered around any of those 150,000 stars, we might be looking back at the Drake equation and going, one of those numbers might be 0 now. But in fact, thousands and thousands of planets were discovered around those 150,000 stars. So thank goodness we're not in trouble there. Here's some of the data from Kepler. As I said, the larger the planet, the slower it goes, the deeper the light curve dip, and the more information you get from that as well. Here you can see that as Kepler came on in the mid 2010s, the number of planets discovered by the different techniques was immediately dominated by transits, because that's what Kepler was good at discovering. And as I said, it requires that the planet orbit in a plane that brings it in front of its star in order for us to use the transit method. And it's estimated that only 1% of the planets around any random set of stars will actually be orbiting in a plane that will bring them directly in front. So you can take this number and immediately multiply it by 100 to say if 5,000 stars out of 150,000 show planetary dips, then there really are 100 times as many planets. They're just orbiting in different planes that don't pass in front of their stars. So at least more than we would initially think. So again, Earth-sized planets are really hard to detect. There's a very small dip, as you can see here in the bottom, but a Jupiter-sized planet would give you a much larger dip. So if some of you want to try this, it's easy to do, with a telescope 8, 9, 10, 11 inches in diameter, and I know a lot of those exist. This is the habitable zone. We call this the Goldilocks zone. A planet that's close enough to its star to be warm enough for liquid water to exist, but not so close that the water exists only as steam or doesn't exist at all. We call that planet in the Goldilocks zone. We're talking about an area around the star. Depending on the brightness of the star, the hotter the star, the farther out the Goldilocks zone is where that planet has to be orbiting in order for liquid water to exist. As far as we know, liquid water is a requirement for life, and we're assuming for now that any life we would investigate in the rest of the universe would be based upon water as well. And Kepler 22 was the first Earth-like planet discovered to be in the habitable zone around its star. You can see that as this green disk here. Anything closer than the green disk would be too hot. Anything farther out would be too cold. And I'll go through a couple of these quickly here. We've already talked about that one as well. Okay, so lots of missions for exoplanet discovery. The one that I've got starred here is called TESS, which is a new transiting exploration mission. This is, here we are, here's TESS. So TESS is going to look at bright stars, but at lots and lots more of them. So TESS needs really bright stars. So you can see that the Kepler mission is going to look at very faint stars down in the lower half of this bar, but the TESS mission is looking at the brighter stars, and it can do it lots and lots faster. And even though we've got lots of data from Kepler, and there aren't as many bright stars as there are dim stars, TESS is still going to look at a really large number of bright stars, even though they're very far away. So TESS has completed its primary mission, looking at the 200,000 nearest brightest stars, and there are about 7,500 candidates that have been identified so far. All right, and then the next step is the Nancy Grace Roman Space Telescope. And this is used to be called the W-FIRST mission. And this mission is actually going to look at a completely different set of stars as well, including what we call free-floating stars, free-floating planets, because a free-floating planet that's warm enough will emit infrared light, and the Nancy Grace Roman Telescope will be able to identify those free-floating planets by their warmth and their infrared light that they emit. And the big goal here is to characterize the planetary environments. Recently, our spectroscopic analysis determined the presence of dimethyl sulfide and dimethyl disulfide in the atmosphere of an exoplanet. And those compounds are typically associated with life, as is something like methane, right? So if you look at the spectrum of light emitted and absorbed by the atmosphere of an exoplanet, you can see these bumps, and these various bumps are associated with different chemical compounds, water here, CO2, oxygen, H2O, and so on. And that will tell you something about the constitution of the, including methane, where you can see the source of most of the methane on Earth is right there. So, yep, there are plans in the future to look for exoplanets with other large telescopes. Well, let's hope that they continue to be funded. So are we alone? We started with this big question. So we know now that 70 to 90% of all stars have at least one planet. There are lots of small planets. Multiple planet systems seem to be the rule. There are some Earth-sized planets in habitable zones. So those are candidates where life could exist today. And we think that over 100 million Earth-like planets exist in our galaxy. So our two numbers, the number of planets around stars is approximately 1 or greater. And the number of planets in the Earth-like habitable zone, or the Goldilocks zone, is probably greater than 0. So we have confirmed that out of the 7 important numbers in the Drake equation, 2 of them at least are not 0. So the odds are not 0 that we are alone in the universe. This little animation was done in 2010. This shows not only the actual sizes and positions of the planets around stars, but it shows them actually in the speed at which they orbit, the relative speed at which they orbit their star. Isn't that amazing? So this was done by Ethan Cruz back in 2011 or 2012. So I love that. I just love this whole thing. So keep looking up. Somebody might be waving back. Oh, thank you very much.
Given the hour, we'll take a few questions, but then we'll kind of cut it short if the questions go long, because we're already a few minutes after 9. So, but anyway, if anybody has questions, please let us know.
Question is, Ted, is there a discovery of a new planet?
Is there, I'm sorry?
Is there the discovery of a new planet that we hear all the rumors about?
A discovery of a new planet, like around the sun? Not that I know of.
They said that they
Yeah, not that I know of. Okay.
I have a question about the Doppler shift or the radial velocity. And then the picture of the Earth as seen above is wobbling back and forth. Does that mean we don't observe much in the ecliptic plane, but like perpendicular, so we don't have to cancel out the Doppler shift?
Okay, yeah, thanks. That's a good question. Now, in that New York Times article, they were talking about the actual motion of our sun as it's tugged sideways around by the various planets. So there would be no Doppler shift in that case at all. That would be somebody who could actually resolve the position of the sun compared to stars behind it and watch it being moved back and forth by the gravitational tug of the planets. So that was strictly motion. In order to see Doppler shift, you would have to be in the plane that the sun was orbiting in order to see it coming towards you or away from you. So yeah, they're two completely different things, and they didn't make that clear in the New York Times article, but thanks for asking.
How do you determine between a spectroscopic binary star and the spectroscopic effect being due to a planet?
I'm really sorry, we're out of time. Great question. I have not considered that, but it's a confounding problem. You're right, because you've got in a spectroscopic binary, you've got two stars that are so close you can't resolve them, but one of them's moving away and one of them's moving towards you. So you see a continual change. Sometimes the spectral lines might exhibit retrograde motion and sort of move over and then go back. Yeah, that might indicate a spectroscopic binary. I think I just got my Nobel Prize for thinking of that so quickly. But yes, you're right. That's a confounding problem, and it's very difficult to tell the difference. Okay, thanks. I'll stay up here if anybody wants to stay late for a few minutes. Thank you again.
All right, thank you, everybody. Have a wonderful evening. Hopefully next month, August 15th, when we have a meeting, we won't have to switch out the laptop 10 minutes before the meeting starts. So anyway, have a good evening.